Alright everybody, we're covering our study of the chapter on energy, which also includes the study of work and power as well. Alright, so this chapter is the newly revamped syllabus, which will you will sit for the exams in 2024. So we'll be discussing energy in new terms, or rather using a new model to explain. Right, nothing else really changes. It's just another way for us to phrase things. Right, so our study of energy will include these few things. What are energy stores? What is energy transfer? What is work done? What is power? And how do we obtain energy? Alright, some prereq knowledge that you should have before the study of this chapter is the knowledge that rather the fact that the weight is equals to mass times gravitational field strength, or gravitational acceleration. So G could be 10 Newton per kilogram or 10 meter per second square. That is the same thing. The units of force is also the Newton. So these are basically all the things that you need to do lah. Alright, so we're skipping quite a bit of slides just for your info, because there are certain things that I think are repetitive, so I will skip some of the slides now. Alright, so energy stores and energy transfers. I highlighted stores and transfers here because these are the new terms that we're going to use. They just different ways of saying the same thing lah, right? So just leave this here. If you want to read about it, something interesting, you can just pause the video. Alright, so what is energy? Energy in the very layman terms is what you need to be able to do work. Right, the unit of energy is the joule, and is written as a big J. So if I want to say I have 10 joules, or I do 10 joules of energy, or I have 10 joules of energy, then you just write it as 10 with a big J, like that. Alright, now we say energy is, when an object has energy, we say it has energy in a certain store of energy. So roughly these are the 6 main ones that you will roughly need to know for your study. So let me just go into detail with each of them. So the very first one we are going to talk about is elastic potential store. So elastic potential store basically happens whenever you deform an object out of shape, and it will try to then revert back to its original shape. So things like stretching a rubber band, squeezing a ball, they want to grow back to its original shape. So it's basically anything to do with deformation of this original shape of the object. Then we say we have given energy, or it has energy in the elastic potential store. Alright, moving on to the next one. Kinetic store is basically anything to do with anything that requires motion, or that has motion. So if an object is moving, we say it has energy in the kinetic store. Alright, internal thermal store, also quite a simple one. Basically anything to do with temperature. So if an object has a certain temperature, then we say it has energy in the internal thermal store. Alright, nuclear store then has to do with nuclear energy. So it is the energy that is stored in the nucleus of the atom, and it is one that we use when we talk about nuclear bombs or nuclear power plants. Basically most of the nuclear stores are usually found in what we call nuclear fuels lah. So things, nuclear elements like uranium, so all these things will have nuclear store. Chemical potential store is basically stored energy in terms of the food, the fossil fuels, or batteries. So all these have chemical potential store. Alright, and gravitational potential store finally has to do with how high you are. So position above the ground. The higher up you are, the more gravitational potential store you will have. Alright, so these are the basic 6 main few. It should be sufficient for you to be able to describe most of the energy transfers that will appear in the exams. Alright, so energy transfers. So you might be useful for you to think of energy as something that can move around from one store to another store. Alright, however, it is important for you to know that the total amount of energy should remain constant. Now, if I have all these different stores, of which you learned there were 6 of them that you should roughly know. If you have these 6 different stores, how do I transfer the energy between the stores? Now, in the model that we are learning, there are only these 4 ways that you will need to know in which energy can be transferred from one store to another. And these are the 4. So I'll just go into a little bit of detail with this, because I also put a star here because this is important for you to know, right? So the first way you can transfer energy from one store to another store is via a mechanical force. So we call it, you transfer mechanically via a force, and that force must act over a certain distance. Alright, the second way you can transfer energy from one store to another store is via heating. And the heating can happen only when you have a temperature difference. Right? You know that energy flows from hot to cold, so when you have a temperature difference, then you transfer energy from one store, from the hot store, from the internal thermal store of the hot object to the internal thermal store of the colder object. Alright, the second one, or the third one, is via propagation of waves. Now, I know there are some things that actually, in fact, most of the things here you have not, things that you will cover in the later chapters. So just take note of them for now and accept it, but it will be clearer once we cover those chapters. So by propagation of waves, there are actually 2 ways in which you can do this. Is via an electromagnetic wave. You will learn a little bit more about this in electromagnetic waves, the chapter you will learn later in the year, or via mechanical waves. Now, mechanical waves, the only one I think you should probably know is sound wave. Now, of course, there are other types of mechanical wave, which just basically has to do with vibrations, right? So, vibration through air, you know this as sound wave, right? You know vibration through water. So, water wave is also another type of mechanical wave, and also actually earthquake is also a form of mechanical waves via the transfer of vibration energy via vibration. Alright, and the last way, which you will only cover roughly in the set 4 year, which is via electrical means. So electrically, by charges moving through a potential difference. Now, the energy transfers that you learn here should be explained using something called an OEA model. So this OEA model basically stands for, first you state your observation that you see for O. Alright, let me just get your observation that you see of the phenomenon, after which you then explain how the phenomenon happens, and then you do an analysis. What analysis are you using? You are doing an analysis of the energy that is involved. Now, when you try to do this OEA model, it is always important for you to strictly define or identify what is the system. Now, what on earth is a system? A system is basically the object you are talking about. Alright, so if I'm throwing a ball and I want to observe the energy, and rather use the OEA model on the ball, then the system I'm looking at is actually the ball, the object basically. Right, so let me run through some of the examples of what it looks like. I won't go through all of them, so I will pause at certain slides so that you can pause the video and have a look and read through. So I'll begin with the first one, energy transferred mechanically via a force. So in this OEA model, we start off first with what you observe. So let me just set up the situation here for you. I have an object that is already initially moving, then after which I apply a certain force and the speed increases. So your observation is a simple one. When an object is pushed by an applied force, the speed of the object increases. Right? So that is simply just your observation. Now, that is your O portion done. Now, how do I explain why the speed of the object increase? The explanation is something that you should be able to explain from things that you have learned in other chapters. Alright, so in this case, speed increase just means acceleration. And when you want to explain why an object accelerates, you are using your Newton's second law here. So Newton's second law states that when I have a resultant force acting on an object, the object will accelerate in the direction of the force. Basically, that is your explanation, right? Now, so now we go into, that is your E done. Now we're going into the analysis of the energies. Now, the analysis of the energies, what you need to do is identify first what energy the system has, which is at the start, what energy the system has at the end, and of course because I use the word system, you must have identified what on earth is the system that you are looking at. So in this case, you are talking about the card. Right, we represent this analysis via a diagram with two graphs and an O in the center to identify the system. So it looks like that. Alright, so at the start, the object was already moving in 1 meter per second, so we know it has kinetic energy. So we draw that it has some kinetic energy. Alright, so this is the initial energy. At the end, the card is moving faster, so you know it has some energy at the end. Alright, so this is the final energy. So you identify the system, then you label what the system it is that you are looking at by putting it into this circle here in the center. Now, all you need to do then is to identify how I get from here to here. And I get there because energy is transferred mechanically via a force. You remember I said there were only 4 ways in which energy can transfer from one store to another store. So you must use those phrasing that was introduced earlier. So to indicate that energy is being supplied to the card, I draw 3 blocks of energy here. I draw an arrow going into the card, which means I initially had 1 block of energy. Now I have a supply of additional 3, which means I end up with 4. So 1 plus 3, I have 4 energy at the end. Alright, so that's basically how you would explain energy transfers under this model. So I'll run through one more example. I think all this is quite easy. So energy transferred via heating because of the temperature difference. I have a block of butter. It's in a pan and I'm heating it up. The butter will melt. Now, so this is your observation. It melts. Why does it melt? Alright, again, these are things that you will be able to answer when you come to the later chapters on thermal physics. But basically, there is a transfer of energy due to the temperature difference, and that temperature difference will then result in energy transfer from a high temperature to a low temperature. So of course, the pan is in contact with the electric stove, so it's hotter. So it's going to transfer energy from the pan to the butter. So the butter will increase in temperature and then therefore that's why it melts. Now, let's look at how the analysis diagram will look. Again, your initial amount, you need to know your final amount and also the system that you're talking about. In this case, we're going to talk about the piece of butter. Alright, so this is how you will go about 2 graphs with the system in the center identified. I identify the system first, it is butter. Since the butter, of course, is not at has no temperature, it must be at a certain temperature. Alright, so it has some internal energy, of which after that, I have energy being transferred into the butter because of heating or temperature difference. So let's say now I draw that 5 units of energy are entering the butter. So I draw an arrow in. So 1 plus 5, I end up with 6. So basically that's it. Alright, so the next few examples are examples of all the possible means in which energy transfers have occurred. So I've covered 2, which is mechanically and also via temperature difference. So the next example is via electromagnetic waves, via propagation of electromagnetic waves. Alright, so I just leave this here. You can have a look at the O, E and A, the observation, the explanation. Alright, pause it at any time. And of course, the energy analysis. Alright, so just do take note when you are going to say propagation of wave, please do specify what kind of wave we're talking about. In this case, it is via transfer of electromagnetic waves, which is the infrared waves. Of course, these are things that you still haven't covered yet, but you will be familiar with these terms when you cover the chapter on electromagnetism. Electromagnetic waves. Right, so moving on. Transfer of energy via propagation of wave via mechanical sound wave. Alright, so I'm just going to scroll through. If you need to pause at any time, just pause. Alright, this is how you would explain how energy is transferred via propagation of wave. You will learn this in the chapter on sound. This is how the analysis diagram will look like. And of course, you must use the terms that we introduced. Energy is transferred via propagation of mechanical sound wave. Alright, all you need to ensure is that the energy here, the sum of this energy here, must be equal to this energy here at the end. Alright, And I will cover the final one, which is electrically. So the system is a simple one. I got a bulb connected in series with battery and a switch. I close the switch, it lights up. I open the switch, it doesn't light up. Sorry, it does not light up. So how do we describe or explain this transfer of energy? The battery basically has chemical potential store. Yes, energy in the chemical potential store. Alright, when the current flows, it will cause the filament in the bulb to heat up. So it will heat up so much that it will start to glow and light up. Alright, so let's look at the energy analysis for this. It is a little bit unique and different from the ones you encountered before. Everything else remains the same. I have the system in the center. In this case, I decided I want to talk about the bulb only. I want to look only at the bulb. So I written this as the bulb. Now, what you define as the system will then affect your diagram. If let's say I want to not talk about the bulb, I want to talk about bulb plus wire plus battery as a whole, then of course your energy diagram is going to look different. Alright, so in this case, I'm just focusing in on the bulb. So the bulb has some temperature. Alright, it is not at 0 Kelvin, so it has some temperature. We say it has energy in the internal store. Then you have the battery being transferring energy electrically from its chemical potential store. So I supply 4 of it. But then you know at the same time that what happens is that the bulb will heat up. So you know at the end the bulb must be hotter than it was. That means it must have more energy in the internal store. So that's why I drew a bit more. But at the same time, you also know that light is being given out by the bulb, and you also know that the area surrounding the bulb, that means the air or the surroundings around the bulb, will also heat up because of the heating of the filament for it to glow. So that means I will say I have 2 units of energy transferred by light and infrared waves. So rather, I don't really like this phrasing because I want you all to use the phrasing that was used is via propagation of electromagnetic waves via light, because light is emitted, and via infrared waves because you feel the heat from the light bulb. Right? So you should use this phrasing here. So at the end, you notice that this is the energy going into the bulb. This is the energy that is leaving the bulb because it's actually going into the surroundings. So you have 1 plus 4, so you end up with 5. But then you have 2 leaving the bulb, which means you are only left with 3 over here. Alright, so you can draw energy coming into the bulb and leaving the bulb, or rather I would say leaving your system, depending on whatever kind of situation that you may have. Alright, so I'm not going to go through this. So if you need to have a read, just pause the video. Alright, so I have all these videos up here. You can go into my slide and have a look. I just want you to realize that actually the system is not so clearly defined. In any kind of phenomenon, there's a lot of objects at play. Like, for example, a rocket taking off. You have rocket fuel, you have the rocket going up, you have the exhaust, you have the dust particles flying out, you have the thermal energy coming out, you have actually light coming out because I can see this. So there's actually a lot of things. So you must identify the system properly, because if not, it will be very difficult for you to be able to draw or describe using the OEA model. Alright, so which brings me to at least the calculation point. We are going to talk about how to deal with kinetic energy and also gravitational potential energy. Alright, before we begin our study, if you have my slides, then you can just go to this my slide here and just click play to go and play. I just want you to watch the video from the start to the 56-second mark. If not, I will link the video in the comments. Alright, so this portion, we are talking about the kinetic store of an object. So in the kinetic store, this is one of the 2 energies that you are supposed to be able to calculate at this juncture in this chapter. Later on in the thermal physics chapter, you will learn how to calculate another form of energy. But basically the kinetic energy, let me change the color. The kinetic energy of an object is given by half mv square. Just take note that the square belongs only to the v and not this. So it is just half mv square. Now, the kinetic energy, of course, energy is measured in joules. The mass of the object must be in kilogram, and the speed of the body must be in meter per second. Alright, so just to show a simple example of how to calculate kinetic energy, if I have a mass of 1 kilogram moving at a speed of 2 meters per second, then I just apply the formula half mv square. Half the mass is 1 kilogram, the velocity is 2, I square it, and I end up with an answer of 2 joules. Alright, so 2 times 2, 2 square is 4, 4 times half is 2. So that's how I calculate kinetic energy. Alright, so here are some examples for you to run through. Please pause the video before I run through the solutions with you and attempt it by yourself. Alright, so I hope you have the answer. Let's go through. 50-gram toy moving at constant speed of 2 meters per second. Let me just change this color again. Calculate its kinetic energy. You use the formula half mv square. Remember that the mass must be in kilograms, so it must be 0.05 kg. You must convert the 50 grams to kilograms. The velocity is 2 meters squares. It's in the units that you already want, so you just 2 square it. And that will give you an answer of 0.1 joules. Just punch that into the calculator. Now, it is important that you pay attention to the units, because the units will determine whether you get it wrong or right. A lot of students will end up not converting it to kilogram before the calculation, or if the units was given in kilometers per hour, they don't change it to meter per second before the calculation. Alright, so the next energy that you should be able to calculate is gravitational potential energy. So I would like you all to go and click on this video. It's actually the same video as the kinetic energy one, but I want you to now to watch it from the 56 second to the 1 minute 56 second mark. Alright, so gravitational potential store, as you recall, has to do with how high up above the ground. So it has to do with the height above the ground. The formula is given as GPE is equals to mgh. Alright, where m is the mass of the object, g is the gravitational field strength. You say it's 10 newtons per kilogram or 10 meter per second square. You can use it interchangeably. The height must be in meters. Alright, so a simple example for you to calculate. I just give you a little bit of complication. You have to think about it. I have a boy, 60 kilograms. He climbs up from level 1 all the way to level 5, and each floor is 2.5 meters tall. Please calculate the gravitational potential energy that the object, rather the boy has. Alright, so pause the video now. Make sure that you do the calculation before you come in and check. Alright, so the mass of the boy, you use the formula mgh. The mass of the boy is 60 kilograms. Gravitational field strength is 10 newton per kilogram or 10 meter per second square. Height, now this is a little bit tricky, so just take note, level 1 to level 5. Level 1 to level 2 is 2.5. 1 to 2 is 2.5. 2 to 3 is another 2.5. 3 to 4 is another 2.5. And 4 to 5 is another 2.5. So all in all, it's actually 1, 2, 3, 4. You go up 4 different levels. So 4 times 2.5. Alright, so it's 60 times 10 times 10. And that will give you an answer of 6,000 joules. Alright. So please attempt this question. Come back when you are ready. Alright, so how to calculate this? Just apply mgh. Mass is 5 kilograms. G is again 10. It should be given in the question. And the height is 50 meters. Alright, simply that will give you an answer of 2,500 joules. Alright, next question. Or no more next question. Just a summary of what we have learned so far. So this will be important for you. So I put a star down here because I feel that this portion here, or the summary, is a good summary here. So what is the definition of energy? Energy is something that is required for you to be able to do work. Alright, energy can be transferred. I can transfer it from one store to another store. And there are only these 4 different pathways that you need to know. One is via the mechanical means. That means physically a force acting over a distance. via heating when there is a temperature difference, via propagation of waves, of which you know there are two different type of waves that you need to know: electromagnetic waves and mechanical waves. Alright, the last one is electrically via charges moving through a potential difference. You need to know how to calculate using the formula for kinetic energy. Kinetic energy is equal to half mv square, and gravitational potential energy is mgh. Alright, so we'll move on to the next portion of the lesson, which has to do with the principle of conservation of energy. Alright, please watch this video. For those of you who have no access to my slides, I'll link the video in the description below. Alright, so the principle of conservation of energy is an important conservation law. So the principle of conservation of energy states that you cannot create energy, you also cannot have energy disappear out of nowhere. So if you, let's say, have a match that you're going to strike for you to start a fire, for it to light up, so the total amount of energy you have before and the total amount of energy you have after must be the same. So this is what you all have already covered in your study earlier of the OEA model. That is, the energy at the start must be the same amount of energy you have at the end. Alright, so even though I have energy being transferred from one store to another store, the total amount of energy in that system must be the same. Alright, so this basically, I think you need to memorize word for word. Alright, so the next time you see this, is just me being lazy and not saying principle of conservation of energy. So POCE basically states that, and you should remember this word for word, energy cannot be created or destroyed. I can only transfer energy from one store to another store of energy. The total energy must remain the same. So these 3 points altogether compose of what we call the principle of conservation of energy. Constant or the same. Alright. So the most and how we usually describe is via an ideal pendulum. An ideal pendulum is one where the pendulum does not lose energy due to friction, which means there's no air resistance. That means there's no friction at where the pendulum is being held up. Alright, so when the pendulum is swung up, it is given energy in the gravitational potential store. When I release it, then all that energy in the gravitational potential store is transferred to the kinetic energy store when it is over here. And how it is transferred is by a mechanical force, which is actually your weight. Your weight is the one that is pulling it down. After which, the kinetic energy will then allow it to go and travel further, and the kinetic energy in the kinetic store is then transferred to the gravitational potential store. Now, if I do not have any energy being transferred out of the pendulum due to air resistance, that means I have no energy being converted to internal thermal energy, then in theory, an ideal pendulum will then be able to oscillate forever. Alright, so this is just the diagram of what it will look like. In an ideal pendulum, the gravitational potential energy will entirely all be transferred into the kinetic energy store. Alright? And when the kinetic energy store is when it's at the most bottommost point of the pendulum, at this point it has all the kinetic energy. Then as it travels up, this kinetic energy is transferred from the kinetic energy store to the gravitational potential store. So it rises up to this point. So everything is here. Now, of course, you know that this is not really the case in real life. So what happens if we do not have an ideal pendulum? That means you introduce the fact that there are resistive forces such as air resistance. Alright, so let me just show you what it should look like in this portion here. So let's say I have a pendulum. It is not an ideal pendulum. It is a normal pendulum. My system is identified here. It has kinetic energy of this amount, and it is now going up to this point. Right, which means actually not all of the kinetic energy is going to be fully transferred over to the ideal pendulum. So let's say one of it is lost to the surroundings, to the air, because of air resistance, which means I initially had 5. Now I have 4 only in the gravitational potential store, which means I need to draw then that I have 1 block of energy leaving this system, and this block of energy is via a mechanical force, and that mechanical force is your air resistance, and it's transferred into the surroundings. Alright, so the energy still is not lost. The principle of conservation of energy is still maintained. Whatever energy I have here is still the energy I have here. Alright, it's just that it doesn't stay in the system. My energy has left the system to go into the surroundings. Alright, so I'll leave this here. I know it's going to be a long video, so if you want something to look at, just take a break and watch this video if you want to. Alright, just look at what are all the points that this person is saying. I won't go through this. You can pause if you want to. Alright, I think I left a blank here. It is not supposed to be a blank. Let me fill this up. Alright, energy is transferred from the lights to the surrounding via propagation of electromagnetic waves. Alright, so you can read the solution here about the robot. Now, the most important part about principle of conservation of energy, of course, have to do with the calculation. So let me go through the calculation with you, or if you want, you can just attempt. Just pause the video and then I'll show you the solutions after this. Alright, so I have a ball of 500 grams. It is being dropped from a height of 10 meters. Calculate the gravitational potential energy. Right, quite simple. Just use the formula that you learned, mgh. The mass is 0.5 kilograms. Remember, I need to change the grams to kilograms. G is 10. It should be given in the question. Unfortunately, I didn't type it in this one. Alright, and my height is just 10 meters. It's already meters, so there's no need to convert anything. And I'll get the answer as 50 joules. Now, they ask you then what is the velocity of the ball just before it hits the ground. Now, you know from the principle of conservation of energy that whatever GP I had at the start, or rather energy in the gravitational potential store, must all be converted to the kinetic store. So whatever I lose in the gravitational potential store must be whatever I gain in the kinetic store. So since I know how much energy I had in the gravitational potential store, I also know how much I have in the kinetic store just before it hits the ground, which means that I can just say it's 50 joules. So the kinetic energy just before it hits the ground should be 50 joules because all of it came from the gravitational potential store. And then I just put in the numbers. Mass is 0.5, then V is what I want to calculate, V square. Just do your manipulation, algebraic manipulation, and you get the answer 14.1 meter per second. Alright. Okay, we'll practice another question here. Again, pause if you need to. I'll go through the solutions. Alright, so I have a ball being dropped 500 grams from a height of 10 meters. So I have a ball here, and there is an energy transfer, they tell you, of 10 joules mechanically due to the air resistance. Then they ask you to determine the velocity. Now, this is the mass. The ball only has energy in the gravitational potential store. Alright, at the end of the day, just before it hits the ground, it should have kinetic store. Alright, but they are telling you that I lose some of this energy due to air resistance, meaning it is transferred out of the ball into the surroundings. So first and foremost, I calculate. It is exactly the same calculation as before, so I can use the same formula to calculate. I'll get the answer of 50 joules. Just use mgh. Alright, so by the principle of conservation of energy, I now then can make this statement. Whatever energy I had at the start, which is just your gravitational potential energy of 50 joules, it must be the energy it has at the end plus whatever energy I transferred out of the system. So I will say the term energy loss, energy transferred out of the system into the surroundings. So 50 joules is just your final KE plus the energy loss, which will tell you is 10 joules. So 10 joules. which means I then know my kinetic energy just before it hits the ground. 50 minus 10, the answer is 40 joules. After which, then all I need to do is then do the same steps as I did in the previous question. 40 joules is equals to half, m is 0.5 kilograms, velocity square. I can then use my algebraic manipulation, calculate the answer, 12.6 meter per second. Now, if you compare the answer here and the answer here, it makes sense because this object is traveling slower. It has less kinetic energy compared to the previous case where I did not lose, or rather I didn't have any energy being transferred out of the system into the surroundings. Alright, over here I have energy being transferred to the surroundings, that's why my speed is less. Alright, your last question, please do attempt first before you have a look at the solutions. Alright, so I have a 500 gram ball again. Instead of throwing it, I am now instead of just letting it drop, I am now throwing it vertically down. The initial height of the ball is 10 meters, but then I'm launching it down instead of releasing it. So at this point, it has energy in the gravitational potential store, and it also has energy in the kinetic store. Alright, so they say it hits the ground and then it bounces back up. It then rises only to a maximum height of 8 meters. At the maximum height, the ball should then be stationary again. So you know that over here, the kinetic energy is 0. Right? There is no energy lost due to the air resistance, or rather energy transferred out. So then my statement then becomes this. So my solution statement for principle of conservation of energy states the energy cannot be created or destroyed. So whatever energy I had at the start, of which I have two, gravitational potential and kinetic. So initial gravitational potential, initial kinetic energy must equal to the final kinetic energy I have, the GPE I have at the 8 meter mark, and also the energy that is transferred out of the ball at the moment that it hits the ground during the bounce here. Alright, so this is my principle of conservation of energy statement. Alright, of course I know, and I've already told you, the kinetic energy at the 8 meter mark is 0 because that is where it reaches its maximum height. So I know this is actually 0. Alright, so then I can just plug in all the numbers. Gravitational potential energy is mgh. My kinetic energy is half mv square. My final KE is 0, so I don't bother, it's just 0. GPE is just mgh plus my energy transferred. Now the energy transferred is what I want to find, so then I just plug in the numbers basically. Alright, so let me just do this calculation. This is 0.5. The height, gravitational field strength was 10. The height was 10 plus half mv square, half 0.5. My velocity is what was it launched at? 5. So 5 squared, that's the amount of energy I have, is equal to 0. I'm not going to write that down. mgh, which is 0.5 times g, 10, times the height, 8, plus the energy transfer at the bounce. So just punch these numbers into the calculator. You get that the sum of these two is 56.25 joules. This number here is 40 joules, which means that allows me to then calculate how much energy is transferred, which is actually 16.25 joules, or 16.3 joules to 3SF. Alright, so that brings me to the end of the principle of conservation of energy and the energy transfer model via the OEA. So the next one we're going to cover is actually on work done. Alright, the next portion we are covering is on work done and power, and what exactly it means for there to be work done, and what exactly it means what power actually is. Alright, so if you have the slides, just have a look at it. So this is just some things that we need to think about when we are discussing this chapter, or this portion of the chapter. So let me just bring to your attention a situation like this. I got a guy exerting force F on a tree. The tree is not moving, obviously. Alright, and I have a lady here pushing with the same force F on the stroller, but of course the stroller is moving in the direction that she's pushing. Now, in both situations, do you think that they are both using up energy? But what do you think about work? If you think about work in the loosest term, in terms of the definition, is the guy doing any work, or is the lady doing any work? Alright, so these are some things that we need to think about when we talk about work. So let me define what work is. Work done by a constant force acting on an object is the product. Means I multiply the force and the distance moved by the object, and this distance moved must be in the direction of the force. So when I apply a force and the object moves, and it moves in the same direction as the force, then I would say there is work being done. If the object doesn't move, then there's no work being done. So if I look at this, I will say yes, the lady is doing work, but the guy here, he's not doing work. But then you think about it, isn't he expending energy? He's using up energy, right? So we'll discuss this a little bit more later. Alright, so for work to be done, the force and the direction it moves must be in the same direction. Alright, so if we look at the formula for work, it is written as work done. Let me change the color again. Work is equals to force times distance, Fs. Now, why is S written as why is distance written as S and not just D? Is because it is a specific direction, so it is somewhat like a displacement. Alright, work, the unit is in joules. Then you think about it, didn't I have a quantity that is exactly the same that we learned is also joules, which is energy? Force is in newtons, the distance moved must be in meters. So the SI unit for work is actually the joule, which is the same quantity, same unit as energy. So work done essentially is how much energy is being transferred. Alright, so let me give you an example. I have a kid here. The kid is moving, carrying a big bag like this, and he is walking to school along a straight and horizontal road, level road. Once he reaches the school, he climbs the stairs. So is there work done by the student on his school bag? Alright, so when you are thinking about it, if you're thinking about the bag is being held up by a force, which is because of the shoulder straps of the kid. The shoulder straps are the bag on the kid's shoulder. Right, so the student does exert an upward force on the school bag. However, the student does no work on his school bag, because that means that he is not transferring any energy. Remember, work done is equal to energy transferred here. So the kid is not transferring any energy to the bag. Alright, if he's already moving with the bag, that means the bag gains, or rather the system is the bag. There is no energy transfer, that means the bag doesn't gain any energy. Now, however, when he starts going up the staircase, the distance he starts to move is in the same direction as the force. Only when he's climbing up the staircase is there work done. Why so? Remember, work is energy transfer. That means the bag in essence has gained a form of energy. If you think about what energy the bag has gained, because the bag has now moved higher, the bag has gained energy in the gravitational potential store. So only when the distance moved is in the same direction as the force, because the bag is feeling a force upwards due to the shoulder straps, only when it's the same direction, then we say there is work done. Alright, so let's look at a sample question here. I have a car moving with a certain force of engine, 10,000 newtons. It accelerates from 30 meter, from rest to 30 meter per second in 10 seconds. So I need you to help me determine what is the work done by the car. And after that, the kinetic energy at the end of 10 seconds. Now, this one integrates a little bit of kinematics. So this kind of question is quite common. First and foremost, to find the work, I need to find the distance, because work equals to force times distance, right? I only am given final speed, initial speed, I'm given time. Now, how would I go about doing this? The simplest is actually, and this is quite common, so when you see this kind of question and it looks like you don't have enough information to solve, just draw a graph. The velocity time graph. At time 10 seconds, he would have been now at 30 meter per second. So he started from rest, then you just draw. And from your study of kinematics, you know the area under this graph is actually the distance. Then that will allow you to find the distance here. So from kinematics, first and foremost, the distance traveled by the car, we will solve this one first. The distance traveled by the car is just half this area of the triangle, half times 30 times 10, and that will give me 150 meters. So now I know that actually I have the force here. So once I have the force, I can actually find the work done. So let me just skip a little bit here to this portion here, because we don't actually need the mass yet to go and calculate. It's only when we're doing the kinetic energy that we need to calculate mass, because remember the formula for kinetic energy is equals to half mv square. So we tackle one by one. So let me just move down. The work done is just the force times the distance. The force was given in the question as 10,000 newtons or 10,000 kilonewtons. Alright, then you multiply by 150 meters here, then you'll get the energy. The energy is 1,500,000 joules, or 1.5 times 10 power 6 joules. Now I find the work done. Now the next portion of the question asks you to find its kinetic energy. So remember, kinetic energy, I need to find the velocity, and I need to know what's the mass. I already know the velocity because I know the final speed is 30 meters per second. So I only need to find m. So how would I go about finding m? First, use the formula A equals to V minus U over T to go and find the acceleration. So final speed is 30, initial speed is 0, you divide by 10, you know that the acceleration is 3 meters per second square. Now, I know that the force exerted on this is 10,000 newtons. So using your force is equals to MA, you know that the force is 10,000, you divide by the acceleration, you know now that the mass of the car is 3330 kilograms. So now I know the mass, I know the speed at the end here, I can then find the kinetic energy. So the kinetic energy can then be found, it is just half times the mass, which is 3330, then you velocity square, which is 30 square, and you get the answer 1.5 times 10 power 6 joules. Now you compare this number and this number, then you realize that actually this is the same number. So what you have essentially calculated is the work done by the car is actually equivalent to the kinetic energy that the car gains. That means how much work is done by the car, or rather the engine of the car. Remember, work done is just energy transferred. All the work that is done by the car is transferred into the kinetic energy of the car. That's why these numbers are the same. Alright, so work done is equal to the kinetic energy. Now, another similar type question that can appear is this kind of question. Always appears in the MCQ. So basically I have a box, 1 kilogram mass, being pushed by a force along the slope, direction of the slope. The box ends up at a position 4 meters above the ground, and they ask you to calculate F, and they ask you to ignore friction. That means there are no other forces. That means the only force at play is this one, and of course the weight downwards lah. Alright, so now let's look at it. The only thing that is causing this box to move upwards is this force here. So you know that the work done on this box is the energy transferred to the box. So if you look, and you may think that you do not have enough information to solve this question because you don't know what kind of energy it has gained. You know that the box has gained 1. You must have gained gravitational potential store because it is higher, but you have no information about the kinetic. Alright, they never tell you anything about the speed at the start, at the end. So whenever they never mention anything about the speed, then it's easy. You just assume that they move slow enough that there's no change to the kinetic energy. Alright, that means the box is moving so slowly that the kinetic energy hardly changes along the slope. So that means all the work done, or rather all the energy transferred, goes almost entirely into the gravitational potential store of the box, which means now I can make this statement: work done is equals to the GPE of the box at the end. And I know how to calculate the GPE of the box at the end. It is just mgh. The work done is just force times distance. Alright, so what is the GPE of the box? The box is 1 kg times 10 gravitational field strength times height of 4. The force is the one that you are supposed to find. Calculate F. The distance, that remember that the distance moved must be in the same direction as the force. So if the force is moving in this direction, that means the distance we are using is the 5 meter. So force times 5 meters. So what I have now essentially is phi F is equals to 40. So F is equals to 8 newtons. So now I found the answer. Alright, so that is work done. It needs a little bit of digesting because it is a little bit of a weird concept. But what I need you to hold in your head, and very importantly, is that work done is just the energy transferred. So whenever I do work somewhere, someplace, in a certain form of an energy store, somebody must be gaining the energy. Right? So let's move on to this consideration. We are moving on now to power. So let's look at this situation. I have two boys of the exact same mass. Boy A and boy B are both climbing the same distance from here to here. Boy A, however, took a much shorter time to climb up the stairs. Boy B took a much longer time. So now if we look at it, the boys both have the equal mass and they travel the same distance. Therefore, the work done is the same. Alright, but boy A took a shorter time to reach than the second boy, which means that boy A exerts more power. Alright, so we'll discuss what power is very quickly. Basically, what it means is that boy A is doing the same amount of work, but he's doing it in a much shorter time. So that is in essence what power is. So what is power? Power is defined as the rate of work done or the work done per unit time. So it's just work done or energy transferred per unit time. So the SI unit of the power is now something new you have to remember. It is the watt, written with a big W. Alright, 1 watt is also known as 1 joule per second. So the equation for power, and I'm going to put a star here because I think this is important. For this whole slide, it's important. Power is just work done over time. Alright, the work done over the time it took for the work to take place, or energy over time. Because remember, work done is just the energy transferred. Alright, so let's look at examples. And power is more commonly seen in your electrical appliances, even your electrical bill. So we'll cover a little bit more about that in your chapter on electricity. So for example, let's look at this question. I have a 1500 watt kettle. So they're asking you basically what it means when it's 1500 watts. That means this kettle is able to deliver 1500 joules every second. That's essentially what it means. That's what a watt means. Now, so let's look at the question. Sorry, I just wanted you to take note. I think I missed this out here. The time must be in seconds. This is important. So let's look at a simple question. You can pause and you can attempt the question first before getting back here. Alright, so I'm going to run through the solutions of this question. An engine does 6,000 joules of work. It does this in 10 minutes. What is its power? Power is just work over time. the work it does is equivalent to the energy here is 6,000 joules. It does this in 10 minutes. Remember that the time must be in seconds, so I need you to convert this to seconds. So then all I have is that it is 100 watts. Remember, 100 watts means 100 joules every second. That means this engine is supplying 100 joules of energy every second. Alright, next question. You can pause here and attempt. Get back to here, I'll discuss the answer. Alright, a kettle is rated at 1850 watts. They ask you to determine the maximum amount of thermal energy it can generate in 1 hour. So again, power is just energy or work over time. The power is 1850 watts. The energy is what I want to calculate. The time is 1 hour. Remember, must change this to seconds. 1 times 60 times 60. So do your algebraic manipulation. You get the energy as 6.66 times 10 to the power 6 joules. That means if you switch on a kettle that is rated at 1850 and you switch it on for 1 hour, then the amount of energy that this kettle is going to transfer to either this water inside or the surroundings, all in all, will be this amount of energy that is going to transfer. Alright, so the last concept that we're going to cover is the concept of something called efficiency. So in efficiency, what it means is that in an idealized state, we want how much energy we put in to be how much energy is given out by the machine. But in reality, you know that's never the truth, because there's always frictional forces, there's always air resistance, there's always friction in the machine parts. So your useful energy, that is what you intend for the machine to do, is always less than how much you actually put in. So the efficiency is a measure of how efficient the machine is. So the efficiency formula is given as such. It's the useful energy output over total energy input multiplied by 100%. So let me give you an example. So I have a machine, let's say a car. I put in fuel. The fuel energy is the amount of energy that the fuel can actually give is, let's say, 200 joules. Alright, but the car only gains 100 joules of energy. Rather, the useful energy output is only 100 joules. So if I were to calculate the efficiency of this machine, it is just the useful energy output, that means how much is utilized, over how much energy I actually put in, I times by 100%. That will give me an efficiency of 50%. That means the machine is 50% efficient. Alright, so why is efficiency important? Because we need to examine when an object or an engine or a certain machine or device is not efficient. So if you look at it, this is just some information. Our power stations in Senoko, it actually, you know that it is powered via burning of fossil fuels or crude oil. They burn it and then it heats up water, and the water is then used, the steam that rises is then used to turn the turbine, and that generates electrical energy. Now, not all of that energy that is released from burning is used to heat up the water. Some of it is used to heat up other things, some of it is transferred and dissipated out, or rather transferred to the surroundings. So these are non-useful energy outputs. So the amount of energy that can be used to power electric motors and lights is only about 40 to 50% efficiency. Right? So let me just ask you to, there's a question here, an example of efficiency. Please just do a quick calculation. Alright, so I have a motor rated at 1 kilowatt, which is just 1000 watts. It is a 40% efficient machine. They ask you to find the amount of useful energy in half an hour. Alright, so if I assume that it's a 100% efficient machine, then I can use the formula power equals to work done over time. So work is equals to power times time. Work is 1000 watts times the time it takes, half an hour. Half an hour is just, remember, must be in seconds. 30 times 60, I convert it to seconds, and I get 1.8 times 10 to the power of 6 joules. This is the amount of energy, useful energy output, if the machine was 100% efficient. But the machine is not 100% efficient, it's only 40% efficient. So what I need to do is just take 40%, multiply by the energy that is actually supposed to be there. Alright, 40% is just 40 over 100 times 1.8 times 10 power 6, and that will give me a value of 7.2 times 10 to the power 5 joules. So while I may supply this amount of energy, input this amount of energy, the useful energy output is only this amount, which is less than this. Alright, so hence the useful energy output is just 7.2 times 10 to the power 5 joules. Alright, so the last one is just the different avenues of energy sources that we have. So let me run into it very quickly. Alright, so in Singapore, we need to think about this thing called an energy trilemma. So let me run through what is an energy trilemma. So a trilemma is basically like a dilemma, but there are 3 factors to factor in. So when we talk about energy in Singapore, one of the things that we are considering when we are talking about energy is sustainability. So we want the energy resources to be renewable, and we want it to have as little impact on the environment as possible. Alright, so some of the things that we are considering is solar power, which is renewable and doesn't have any negative effect or too much negative effects on the environment. So that's why we are investing and researching on solar power. So that is what we are doing on sustainability. But at the same time, we also have certain needs that we need to consider apart from just being environmentally sustainable. We need to make sure that our energy is secure, because we don't have energy, basically a lot of things cannot run in Singapore. The lights won't work, you can't go to school because your teacher doesn't have a PowerPoint slide, you can only use markers and pen, right? So energy security refers to how secure the energy is. We don't want our energy supply to be disrupted. Alright, so that's why the way that the government does it is that we diversify our energy resources. So we have many different forms of energy resources to power our energy needs. So we have natural gas, we also have fossil fuels, we also have quite a bit of different needs. So we need to diversify to ensure that we are not dependent on just one form of energy source. And finally, we are going to talk about competitive pricing. Because at the same time, while this is the ideal state where we can just get energy from solar power, we know that the technology is not there yet, and it may cost a lot of money to implement. So that's why we need to think about competitive pricing. Because if not, you want to switch on your light, it's gonna for let's say 1 hour, it's gonna cost you $200. Then nobody's gonna switch on the light lah, right? So we need to remain competitive. So we need to open, that's why you notice that we have opened up the retail electricity market. We have different companies supplying energy. So we can look, basically the customer, which is us, can look for a certain company to provide the energy depending on what we need lah. Alright, so you can just watch this video for a little bit, and let's consider where are the different energy sources coming from. So the first, and you probably would have heard of this, is fossil fuels. So fossil fuels are just petroleum or natural gas, wood and coal. Alright, so because they are forms of chemical potential stores, when we burn them, the heating, remember, because of temperature difference, allow them to transfer this energy from their store to other different forms, which we then convert to electrical energy. Now, what are the advantages of using fossil fuel? It's more reliable, right? It does not depend on certain environmental factors, which I'll go in later, because certain energy resources actually are dependent on the environment around them. They are relatively cheaper, the cost of production, and we already have the infrastructure present, which means we already have the power plants present to go. It's already built, predicated that we are using fossil fuels to power the power plant. Alright, some of the disadvantages is that it's non-renewable. Once we are out of it. And of course, pollution from the gases produced during the burning process. Alright, so that is one of the energy resources that we tap on. Now, nuclear fuels. Nuclear fuel, basically what nuclear fuels are, there are certain nuclei that will undergo reactions, and when they undergo this reaction, they release an intense amount of energy. Right? Things like uranium, they undergo a reaction called nuclear fission. Right? So in nuclear fission, what happens is that the nucleus of the uranium will split, and when it splits up, it will transfer a large amount of energy, and the energy is then used to heat up water. And this water is surrounding the fuel rods, or rather the nucleus, the chamber containing the nucleus. And because it heats it up, the hot air, the water changes to steam, and then the steam will rise up and it will turn the turbine, which will then generate electrical energy. Alright, so what is the good things about it? It has a low carbon energy resource, which means it doesn't emit too many things. It doesn't emit a lot of gases because there's no burning. It's just heating up water via the release of energy from nuclear fission. It's reliable because it's uninterrupted power. However, one of the things we need to take note is that it's not renewable because we have a limited amount of radioactive, or rather fuels that can go nuclear reactions. Another problem is that the risk of accident is when the accident happens, it is quite bad. So the most recent one is your Fukushima one. Alright, so I have a video here, you can have a look at it. It's about Fukushima now and how they have to deal with the radioactive waste, and it's also costly to remove and dispose the radioactive waste. Alright, so that is nuclear energy for you. Alright, now we talk about biofuels. Biofuels are basically things like ethanol, biodiesel, and biogas. So where do these come from? They come from things called biomass, and biomass basically are things that come from living materials such as corn, animal manure. So biofuels have energy because they have chemical potential stores. When you when you heat it up, right, it will transfer this energy into the internal stores of the food and the surrounding. Now it is of course renewable because we have a large amount of it, right, and we are continually growing it. It's widely available and it's actually cheaper compared to other resources. The only problem is that the environmental pollution from the gas during burning will contribute a lot to global warming. It's the same as fossil fuels, right? Now we go into the renewable energy sources. We have wind. You know, this is a wind turbine. A wind turbine, it takes the kinetic energy of the wind, transfers it into a turbine, and it turns, and that turning will then be able to generate electrical energy. Alright, it's renewable, it's clean, meaning it doesn't have any negative effects on the environment. What it does is that the energy is not as consistent as we would like, because you must have wind blowing. If there's no wind, then you have no energy lah. Alright, there are also claims of noise pollution, and also if you have to clear the area to build your wind turbines, then actually it's a loss of habitat for the wildlife in the area. Alright, so that's wind turbines. Now we talk about tidal power stations. Tidal power stations is actually using the high tide and low tide, the water movement caused by high tides and low tides. Alright, so when it's high tide and it rises, then it will cause these turbines to actually spin, and then when it's low tide, then it will spin again. So this spinning effect will then cause electrical power to be generated. Now, because we have a cycle of high tides and low tides, and it is renewable because it has no impact, our tides will always be there. It is definitely more reliable because we always have high tides and low tides. It's clean. However, the negative effects is that it's expensive to build these tidal barrages or turbines. At the same time, the marine life around there, because of the large mass that you're going to put into the sea, so that you can harness the energy of the tides. The marine life in the area will be affected by the changes to the water current and the noise. Alright, so that is tide. We got hydropower. Hydropower is gaining energy from hydroelectric dams. So when you build a dam, you store water up here. When you want energy to be generated, you slowly release the water. You have turbines here. The turbines will spin because of the dropping water, and then you generate electrical energy. Now, it is a renewable source of energy because the energy is always there. There's always water being held up there. It is clean. The only negative effect is that it's expensive to build a dam. Not possible, but I think there will be damage to the environment when you are surrounding a river, when you dam the river in the first place. Alright, we have geothermal reservoirs. These are basically areas like hot springs. You have a lot of water and steam rushing out. If you build a turbine on top of that, then it spins the turbine as it rushes up naturally, and then it will generate electrical energy. Alright, this is renewable. It is clean because it has no negative effect. We're not burning anything. However, I wouldn't say this is exactly correct, environmental pollution, because I mean it is going to happen whether you put power station on top of it lah. It is, the only problem is that not everywhere will you be able to find hot spring. Only certain regions will you have hot springs, and then you will want to harness it there only. So it can only be generated over a small area. Alright, and finally, is it finally? Yes, finally we're talking about solar power. Solar power is basically energy that comes from the sun. The sun basically is a big nuclear reactor lah. The energy in the nuclear store is being transferred via electromagnetic waves from the sun to the earth. And basically, if you have a solar cell there or solar panel there, then it can then harness the energy and convert it to electrical energy. Alright, it is renewable, it is clean. There are no too much negative effects for this. Alright, the only problem is that you got light, then you have electrical energy. You don't have light, then you don't have any electrical energy. Alright, and at the same time, you need to have space for you to generate solar panels. So that's why in Singapore, this is not really very feasible because our land area is quite small. So we need to have really either very efficient solar panels, or we need to have them be placed in places that will allow us, we don't have enough land for us to place solar panels to generate the electrical needs that the Singapore needs lah. Alright, so with that, I think we have come almost to the end of the chapter. Alright, so I think you can watch this video about how we overcome our electrical challenges, energy challenges, and this is a mind map of the chapter. So we are done with this chapter. So if you have any questions, you can just drop me a message via Google Classroom or via the usual means. I will answer them if I can. Alright, thank you. Bye bye.